Hello, welcome to the Principles P6 walkthrough. That's this outcome here that I'm highlighting. First thing, we go into multisim, and when you look at the circuit in the assignment, you're going to see both a parallel and a series circuit. The more difficult one of the two is the one that I'm going to walk you through, and that's the series one. We get the capacitors from here. Once again, I use green ones because you can change their value very quickly, so it's good for quick simulation. We've discussed this before, so no need to go over it again. I've set up some voltmeters across each capacitor and also a voltage here. Now be wary, you must use an AC voltage. Although it says 12 volts, its RMS value, which is what the meters measure, is 8.49 volts RMS. The same as in a series circuit with resistors, you'll find that all of the voltage applied is dropped across the capacitors. So if you add up these voltages, you'll see that they come to 8.49 volts. And as usual, it's just a case of hitting the simulation and we get our answers here. And you can use those to test your calculations to make sure that your calculations are correct. That's one of the beautiful things about multisim. Very quick for simple stuff, and you can check it against your work very quickly. So going into the paper resource now, we look at there's the outcome there, and it's for P6 electrical and electronic principles. There's a few formulae you've got to be aware of. This is the formula here that you're going to use predominantly throughout this walkthrough. Q equals charge, and we measure electrical charge in coulombs. C is the capacitance in farads, and V is the potential difference in volts. For capacitors in series, we use exactly the same calculation, product over sum, that we do for resistors in parallel. It's exactly the same, it's just that we use it for capacitors in series. So taking all of these capacitors, I've started with 33 microfarads and 22 microfarads, and I do that particular sum here. And the result of that, 13.2 microfarads, is applied with the 10 microfarad capacitor, and we come out with an answer of 5.6 microfarads. Because it's an answer, you bold and underline it. We come to the next part now, which is to work out the total charge. Now, in a circuit of capacitors in series, the total charge is a little bit like current in a series circuit with resistors. That means it's applied equally to all of the capacitors. When we work out the total charge, the charge will be the same across all of these capacitors. The thing that will change will be the voltage across each of them. The charge is the same. So when we work out the total charge, we use the total capacitance and divide the voltage. As I said before, we have to be a little bit careful with the voltage because we're using an RMS value. And I'll show you here how to work out an RMS value. So for example, the RMS of 12 volts is 0.707 times 12. You would use this 0.707 any time you wish to find the RMS value of a sine wave. 0.707. So the charge is given by that particular calculation. You take the total capacitance and times it by the applied voltage, and you come out with a charge here of 48.1 microcoulombs. We can now find the voltage dropped across each capacitor. It's equal to the total charge divided by the capacitance of each individual capacitor. I'm going to look at the 10 microfarad capacitor. That's that one there. And you see we take the total charge here and we divide it by the capacitance, which is 10 microfarads. And you come out with 4.81 volts. Now this 4.81 volts is akin to this. I did a little bit of rounding up, but that's what it is. Same calculation for the other two capacitors, and your answer should broadly agree with those shown in the simulation. The final thing you need to work out is the energy stored, and the calculation for that, the formula, is half times the capacitance times the voltage squared. So I've taken the 10 microfarad capacitor again. This is the half of the capacitance. This is the voltage squared. We multiply those together and we come out with an answer of 0.1156 millijoules, or 115.6 microjoules. You need to do the same for the other three capacitors. This should give you a good insight in how to proceed with the rest of the outcome. The calculations are very much the same. Goodbye, good luck.